Okay, so welcome to our fourth lecture on propositional logic. We're continuing our study of logic. Today, next lecture after that, probably for the next 2 weeks or no, a week and a half. But last time we learned about the basic definitions for propositional logic. In particular, we learned what a proposition was. And then we learned, well, just to recall, a proposition is a declarative statement that is either true or false. Once we learned about that notion, we learned these basic operations, which I'm summarizing with a truth table, which we also covered last lecture. So if we have two different propositions, say P and Q, the truth value of each of these is either true or false. And with those truth values, then we can use this conjunction, disjunction, conditional, and biconditional operations between the two of them to form what are called compound propositions. So all of these are compound propositions. Okay, and these are compound propositions are propositions themselves. They will have a truth value that is either true or false, depending on the values of the variable or the propositions that you're using in making those compound propositions. Now, in this lecture, we're going to establish what it means for propositions to be logically equivalent. So we know these basic operations, so it might be of interest, and it most definitely is of interest, to understand when different compound propositions are equal to each other. But first, what does it mean to be equal, right? Like with arithmetic and like numerical values, it's pretty straightforward, like 2 is equal to 2, whatever. But with propositions, especially compound propositions, there can be many different values of a compound proposition depending on the variables that we put into whatever operator that we're looking at. So first, we need to establish that. What does it mean for compound propositions to be equal, right? So that means that we need to begin with the definition. So, two compound propositions. Well, actually, we need to take a step back. Instead of talking about what it means for two compound propositions to be equivalent, we need to introduce some terminology for what it means for a compound proposition to always be true or always be false. So I almost missed that point. So not two, let's start with a single compound proposition. So a compound proposition that is always true is called a tautology. Okay, so none of these compound propositions are always true. So none of these satisfy the definition of being a tautology. We'll look at an example after I've finished writing out the rest of this definition, showing that these do exist. So next part, a compound proposition that is always false is called a contradiction. right? So another really important notion. In fact, we briefly mentioned the idea of a contradiction when I showed you that this like famous Euclid proof of the square root of 2 being irrational. We ran into a scenario where all the things in the given argument led to a false statement. So these do exist from that example, but still it might seem difficult to imagine a scenario where you have two propositions that lead to a contradiction, but we'll get there. And then finally, a contingency. Do I want to say this? Yeah. A contingency is neither a tautology or a contradiction. So a contingency is a compound proposition that is contingent on the values of P and Q in question. All right, definition. Let's look at some examples. All right, so maybe example 1, maybe something like P or not P. Example 2, P and not P. And example 3, P or false. Okay, so these are compound propositions. We happen to have the conjunction, disjunction between P and the negation of P, and then we also have the disjunction between P and a false value. So what is the truth value of P or not P? Recall that, I've run out of room over here, but recall that the negation, that is defined as the opposite truth value. Right, so if P is true, then the negation of P is false. If P is false, then the negation of P is true. So P or not P, what's the truth value of that? Regardless of what P is. It's, I think I heard
True.
True, right? Because the disjunction between two propositions is true whenever at least one of them is true. So P or not P, at least one of those truth values is going to be true. So this disjunction must be true. And I'm using this triple equals, but we don't know what this is yet. We'll learn what it is. But for now, let's just say that that means equal. Okay. What about this one, part 2, P and not P? What must be the truth value of that compound proposition?
False.
False, right? And last time we learned that the conjunction between two propositions is only true when they're both true. So how could P and not P both be true? It's impossible, right? At least one of those is false, which means the conjunction between them will be false. And again, we have no idea what that symbol means yet. And then finally, P or false. The truth value of this compound proposition could be whatever, right? Like if P was true, then that would evaluate to be true. If P was false, then it would evaluate to be false. So it depends. This is a contingency. And if you didn't already catch on, this is a contradiction because this is always false. And then this is a tautology. So hopefully these examples illustrate that sometimes compound propositions are more or less forced to be true or forced to be false. And we're going to make use of this notion when dealing with proof writing next week. Okay? But more generally, we can make use of this notion when encountering some statements in programming, which I'll get to in a moment, after we define what this symbol actually means. I guess that's what we're doing next, is defining that triple equal symbol. So hopefully in your notes, you have this table, or you at least either have it memorized or you have it in front of you, because we'll be using it throughout the lecture. Okay, so definition. Two compound propositions. Two compound propositions. I'll use the letters P and Q to denote them. Right, so I'm writing a single letter P and a single letter Q, but I mean that those are like some type of compound proposition, okay? So two compound propositions, P and Q, are logically equivalent written P triple equals Q whenever P if and only if Q is a tautology. So this is what that triple equal sign means. Right, so recall, I wish I had more boardroom when I erased it, but recall that the biconditional P if and only if Q is true whenever P and Q always have the same truth values, or not always. When P and Q have the same truth values, that's when it's true. Right, so maybe I can squeeze it in right here, just so you remember. So here's P, here's Q, true, true, false, true, true, false, false, false. The biconditional P if and only if Q is true when they're both true, false when they differ, and then true when they're both false. So maybe we can, I think the best way to do it is just to give like a simple example, actually. So this is what it means for two compound propositions to be logically equivalent. And we have to remember what the biconditional statement means. So with that, let's do an example and show what logical equivalence means between two compound propositions. Okay. So I'm going to write a claim down. The negation of P or Q, I claim that's logically equivalent to not P and not Q. So with words, this is saying that the negation of the disjunction is the conjunction of the negations. That's what this is saying. This is my claim. Maybe it's true, maybe it's false, but we should be able to verify it. And that's one mental leap that this course is all about, is trying to convince you that if you see a statement that you can indeed verify it yourself and you can check it. So that's our claim. How would we verify it? Well, one technique to verify logical equivalences is to use a truth table. And this is, you can think of this as a proof because it does give an argument why this is true, though it's kind of a, it's not a very elegant proof. It's kind of an enumeration type of proof, as you'll see when I write down this truth table. But nonetheless, it is a proof. Okay. So we're going to make a big truth table. So PQ, true, 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 false, false, true, false, false. So this is enumerating every possible combination of the truth values of P and Q. So then we can look at, let's just recall what the disjunction between P and Q is, or P or Q. So this is true whenever at least one of them is true. So true, 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 false. Okay, so that's the column associated with that. And now what I'm going to do is I'm going to look at the column associated with that, the negation of this disjunction. So negation of P or Q. So these are the values for P or Q. The negation is simply the opposite, right? So not true is false. Not true is false. Not true is false. And then not false is true. So that's the column associated with the negation of P or Q on every single possible combination of truth values for the variables P and Q. So what's left is we need to look at the column associated with this right-hand side. So we have not P and not Q. Okay, so not P and not Q. So false and false would give us an entry of false. False and true. So again, I'm negating each of these statements. So not true and not false. So false and true, that would be false. True and false would be false. And then false and false. Oh, no, sorry. I have to negate them. True and true would be true. So that's the column of this truth table associated with the right-hand side of this proposed logical equivalence. So now, in order to verify logical equivalence, we have to show that this biconditional is a tautology. That, if and only if that, is a tautology. So I don't know if I can fit it right here. I'll try. So not P or Q, if and only if, not P and not Q. So we have to fill in this column here. Okay. So the biconditional between two compound propositions, or any two propositions, the biconditional is only true when they have the exact same truth value. So looking at these columns, false and so false if and only if false, that's going to be true. False if and only if false, again, they have the same truth values. True. False if and only if false, that's the biconditional again. True. And then true if and only if true. True. Now notice that this entire column of truth values for this compound proposition consists of only T, so true. And it's true on every single possible combination of the truth values of P and Q, which means that is the tautology. This statement is always true regardless of the truth values of P and Q. It satisfies the definition of being a tautology. If that's a tautology, then we can write that triple equal sign and we're good to go. And then a little box right here to indicate that our proof is done. This little square box is a way of representing something called QED, which is an abbreviation for a Latin phrase, quod erat demonstratum, which roughly translates to what was to be demonstrated. So we have a claim, we say that we're going to prove it, we provide the information of the proof, QED box, what was to be demonstrated, we've shown the proof to be true, or we've shown the claim to be true, our proof is done. So we'll be seeing a lot of that little QED box in the future. Okay, so in a similar manner, we can prove another version of that. Right? In this claim here, we have the negation of the disjunction. What about the negation of the conjunction? Well, I'm going to leave it to you to prove on your own with the truth table that the negation of P and Q is logically equivalent to not P or not Q. So you prove that on your own. And if you follow the same template, you should be able to do it. Okay. So this is very important for you computer science majors. These two equivalences are called Demorgan's laws. So again, anytime in a math course, whenever you encounter something that is named after someone, it's probably important. So these are important. This is true. I didn't prove it. I'm leaving that to you. And this is true. I did prove it. These two laws together are called Demorgan's laws for logic. And your CS professors really want you to know these. I've even had CS professors in the past bring it up to me to really emphasize these two things for you. But why? Well, at least in my own experience, I've used Demorgan's laws many times when programming. And the specific cases vary, but typically what will happen is I will be programming something, and there'll be some conditional statement that I need to check for before performing some operation. So if there's like an if statement in my program somewhere, and it's like if not this and that, and then do something, right? So this is like where I've encountered it many different times in my code underneath it. So looking at this, if not this and that, whatever this and that are, this is logically equivalent to what? If not this or not that, do something, right? It's like someone just came to my house. Think of my boot being delivered, so I can walk normal, hopefully. Actually, let me pause the video and see if that is my boot. It was not my boot, but it will show up soon, hopefully. Okay, so yeah, you could translate something like you want to say any program if not these things. Well, you can translate that using Demorgan's law to if not this or not that, or something similar. It actually does come up a lot in practice, and I always remind myself to emphasize that to my students when teaching Demorgan's law, because again, maybe you haven't seen this in programming yet, but I assure you that you will. All right, so next step. Well, we've learned Demorgan's laws, and we can establish these logical equivalencies by showing a tautology on the biconditional between left and right of the logical equivalence by using a truth table. Now, there are many logical equivalences that you should know. And in the chat for this Zoom meeting and in the description of the video when I post this to my YouTube channel, I will provide a link to Rosen's Discrete Mathematics and its Applications textbook, and also a page number for this table that I'm about to write down. Now, for the sake of time and for the sake of this entire board, which I don't have much room, I can't write them all down, but I can write down a few that will be useful. So with that, I'm just going to erase this so I have as much room as possible. So these are logical identities. Similar to identities that you might have encountered when taking a pre-cal or trig course, like trig identities, we're going to establish a bunch of identities that we can use to deduce and prove new identities. Okay, so we have P and true. So this is one of these, it's not a tautology, it's not a contradiction, it is a contingency, because the truth value of this conditional, not conditional, this conjunction depends on P, which means that the truth value of this conjunction really is the same as P. And then in a similar fashion, P or false, we already talked about this one, that's simply going to have the same truth value as P. And these are called the identity laws. Yeah. And then also P or true, well, that's always going to be true, right? Regardless of the truth value of P. So that's a tautology. And then P and false, it's always going to be false. So these are called domination laws. Okay. And then another really important one, the negation of not P is just equal to P. So it's just reversing the truth value back to where it came from. This is called the double negation law. Okay. And then also there are commutative and associative and distributive laws that are in that table. I guess I have to write them down, so I'm going to use them in a moment, but like P or Q is logically equivalent to Q or P. And then the same thing for the conjunction. P and Q is logically equivalent to Q and P. So these are called the commutative laws. Just like in basic arithmetic, right? No, it's important to note that understanding the laws of the operations and the variables that you're looking at is important. Not every system satisfies commutative, like the commutative laws. For example, when you get to linear algebra, A times B is not necessarily equal to B times A. And this is an important thing to just be wary of as you go into your higher level mathematics courses. Okay, so we have commutative, and then we should also have an associative law. It would make sense that P or Q or R is the same thing as P or Q or R. So those would be the associative laws. So P or Q R is equal or R. And the same thing for conjunction. So associative laws. And then the distributive law also applies here. And all of these laws you should be prompted to use a truth table or argue why they're true in the Zai book. But realistically, each one of the laws I'm writing down, just write a truth table down for it, and you can argue to yourself why they're true. So next up, distributive. So P and Q or R. I would imagine out of all of these, this is the first one that's not so clear or easy to figure out. But this is going to be P and Q or P and R. And then in a similar fashion, P or Q and R is logically equivalent to P or Q and P or R. And these are the distributive laws. And they might seem kind of confusing to remember until you think back to distributing in a scalar into like A plus B or something like that, just like in algebra. Think of it like this. So for example, the second distributive law, P or times this. So it's P or Q and P or R. So it's almost like it distributes in. Okay. And then we have the Demorgan's laws, and I think that's it. Like these Demorgan's laws together with these, and then one more. So let me actually write out Demorgan's laws again. So not P and Q, logically equivalent, not P or not Q, and then not P or Q is logically equivalent to not P and not Q. So these are Demorgan's laws, and then there's one more I want to mention. And this next star, I just said star. This next law I call star. It doesn't have a name. This is just what I call it. So the negation of if P then Q is logically equivalent to not P or Q. So I just call this one law here star. And it's really useful. The reason why it's useful is that in many instances, when encountering a new compound proposition that you're trying to derive a new form for, you will need to convert the conditional into disjunction and then start doing work. More importantly, for the sake of proof writing, this right here is the form that sets up proof by contradiction, which we haven't really gone into those details yet. But to kind of like prep you for it, consider some mathematical statements like if n is even, then n squared is even, right? If then, the conditional, if P then Q. So conditional statements are great at modeling mathematical statements that are theorems that you might encounter or theorems you might want to prove or claims you might want to prove. So this could be like a statement you want to prove. The negation of it, whatever the truth value of this statement on the inside is, the negation is going to have the opposite value. So when proving by contradiction, you assume the negation of the statement that you want, and then you show that it's going to be false, just like with the square root of 2 proof in a previous lecture. Well, once you have that statement that you're arguing with and you want to negate it, star tells you how to write it. And now that I'm looking at it, it looks weird. Let me make sure that I wrote it down the correct way. Oh, no, I did not write it down the correct way. I knew something was off. I apologize. it's without the negation sign. So the conditional is going to be P or, no, not P or Q. That's star. Can't believe I just forgot that, but as I mentioned at the beginning of the lecture, had some bad news before class and still a little off. But yeah, this is star. This is a rule that we can use to prove what I just wrote down, actually. So now we can just take these as true and use them to derive new logical equivalences instead of using truth tables. So for example, what did I just write down? I wrote down, yeah, this is a claim. I claim that negation of if P then Q is logically equivalent to P and not Q. Now that's the statement that is used when proving mathematical claims by contradiction. The negation of the conditional is equal to this. So if we assume that and do some like logical reasoning and get something that's false, the original conditional must be true. That's the negation of it. And propositions are either true or false. But that's ahead. Let's just argue why this is true. Well, we could use a truth table. There's nothing wrong with that, except for it's kind of ugly and it's enumerative. It doesn't tell me anything. With this, we could use some of these laws to derive it. And that's what we're going to do. So we can start on either side. I'm going to start on the left-hand side. And I'm going to string together a sequence of logical equivalences until I get to the right-hand side. So looking at this statement here, the only law that I've written on the board that we can use is star. We can convert the conditional inside those parentheses into this disjunction. So let's go ahead and do this. So this will be equal to, logically equivalent to not P, for the negation of not P or Q by star. So I've referenced the law. You can go look it up on the on my board. This is easily verifiable for you to check if you have this information. So the next rule, any guesses? We have the negation of a disjunction. Which rule would apply? Demorgan's law, right?
Double.
The negation of a disjunction we can rewrite using Demorgan's law. And that's precisely what we can do here. So this is logically equivalent to the negation of whatever that thing is right there. It happens to be not P. The or becomes an and then the negation of Q. And this is by Demorgan. So we use Demorgan's law to kind of distribute in the negation. So we take the negation of that, the disjunction becomes a conjunction, and then the negation of Q. And then looking at it and looking at my laws, I see that there's one immediately that I can apply called double negation. Right? I have the negation of not P, so that's just logically equivalent to P. And then the rest stays the same. So that was by double negation. Oh, and we've arrived at the other side, right? We started on the left-hand side, equivalence, 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 and now we're on that side. And at each step of those logical equivalences, we've referenced a law by name so that if someone else were to read this, they would be able to follow our argument. We want our arguments to be as clear as possible. And this is clear. We're done. put a little QED box right there, and we can move on. This is true. We've proven it to be true. Now, again, this will be important when we get to proving mathematical statements later. So in your notes, maybe underline that and just remember that it's a thing. Okay. So I think this is a good place for me to pause, take a break from my leg. So I'm going to pause the video. Okay, we're back. And so we just demonstrated how to establish logical identities between compound propositions with truth tables and with stringing together this like table of valid propositional identities available in the Rosen textbook, which I'll have a link to in the description of this video when I post it. Next up, we have a similar task in that we want to argue that this compound proposition, this conditional statement, is a tautology. Now, what does it mean for a compound proposition to be a tautology? Well, regardless of the truth values of P and Q in this case, regardless of their truth values, that thing should always evaluate to be true. And one way of establishing this claim or proving it is to string together a sequence of logical identities that we know to be valid from the table, and then end up with capital T, always true. So let's go ahead and do that. All right, so proof. So this is the compound proposition at hand. So let's start by writing that out. So P and Q implies P or Q. Okay. Now immediately I see that I have a conditional statement, which means I can use that star law that I wrote down. So this will be logically equivalent to the negation of this whole part here, and then or that. So I'm running out of room, but this is logically equivalent to not P and Q or P or Q. And this is by star. The star law. Okay. Next up, I see that I have the negation of a conjunction right here. Whenever I see that, my immediate thought is Demorgan's law. So I'm going to apply Demorgan's law right there. So this will become not P or not Q or P or Q by Demorgan. And from there to there, that's Demorgan's law. Okay. So then we have a bunch of ors, right? And whenever you have nothing but ors, we can do this commutative law, right? We can kind of group them together however we want. So I'm going to group together my P's and my Q's. So not P or not Q or Q. And that's by commutative laws. Okay. And then finally, we're encountering something that we encountered earlier in lecture. Not P or P, at least one of those is going to be true, right? So this disjunction has to be true, because at least one of those is true, right? And then also, at least one of the Q's, not Q or Q, is going to be true. Oh, true or true is true. We're done. Nothing else to do. that compound proposition, if P and Q, then P or Q, always true, regardless of the truth values of P and Q. Done. Okay. So this is kind of hinting at where we're going. Not next lecture, but the lecture after that, we'll get to mathematical statements where we have some conditions on some mathematical object that imply some other conditions. And that's what we want to argue are true. Later on, we'll use the same type of argumentation to show that algorithms are indeed valid and do what they are supposed to do. Right? Now, from Rosen, the textbook that will be in the link to this video, I would imagine that, well, actually, I need to look through the problems, but I will list them out on Blackboard and in the link to this video, not the link, but the description below, a list of problems that I would highly encourage you to work through and maybe ask me about during lecture, because I like to pick problems from this section to put on the midterm. All right, so that will conclude this lecture, and I'll go ahead and stop the recording now.